So let's go with the second session. In the first session, I spoke on the basics of complex analysis, let's say the main definitions of holomorphic function, and this second will be devoted to speak about integration of holomorphic functions, complex integral, the complex integral, integration of holomorphic functions. Entonces es sesión 2. Okay. So as I said in the first session, we have a continuous function defined on an open set U on the path on U, the integral of a function f along the path gamma is defined as the integral from a to b of this complex number. Okay? Of this complex number. So we are going to speak now what happens, for instance, if we use, if we have holomorphic functions here, or what kind of properties of the integral you can deduce from that, or even using the integral, how can you prove that the continuous function is in fact holomorphic, and some properties related about that. So the first result will be similar result of the what is called the fundamental theorem of calculus. It's usually in one variable. In one variable, you know that you want to compute this integral and assume that f is a Riemann integrable function, and if you have a primitive of f, so a function big F such that the derivative is small f, so you know that the value of this integral is f of b minus f of a. Okay, this is the usual Cramer's, let's say Barrow's rule, and it's a consequence of the fundamental theorem of calculus. So we are going to see that something very similar happens here, for instance. So assume you have your continuous function you have there has a primitive. So assume that f of z has a primitive. Primitive f of z. I mean, primitive would be, in this context, a function holomorphic in U such that the derivative is the function f, small f. Okay? Assume you have a primitive. So you're going to compute the integral. You're going to compute the integral. So if you have a primitive here, consider this function. Consider this called g of t. And if you take the derivative of that, this is the usual composition rules, the chain rule applies here. So you have this property here, and if the derivative of big F is small f, this is small f of gamma t times gamma prime t. So it's the expression you have here. So you have a primitive of this expression. Primitive of the expression would be the function g of t. So using the usual Barrow's rule of complex of real calculus into variables, let's say, a slightly modification, you know that it would be g of b minus g of a. And g of b minus g of a if f big F. So the value of the integral will be the one. So if you have a primitive, the value of the complex integral of a continuous function is the primitive evaluated in the end point minus the primitive evaluated in the initial point of the path. So in particular, the integral is independent of the path. So this integral is independent of the path. I mean, this integral only depends on the initial and the end point on the path, not on the precise path you have. Okay? So you have to evaluate the primitive in the end point and the initial point if the function has a primitive. Let's particular case is that gamma is a loop. Having a loop, I mean a closed path. You remember a loop is a closed path. If gamma is a loop, if the function small f has a primitive, the integral must be 0. The initial and the end point are the same, so the integral must be necessarily 0. Okay? Let's make some example. So an example, a basic example, is the following. Take the function z to the n. Z to the n, where n in general assume that is any integer number except -1 for a moment. Okay, and take gamma as a path, let's say a circle around the origin. So for instance, gamma of t must be r exponential of it, where t goes from 0 to 2 pi. So this is a loop. This is a loop here of radius r. Okay? So let us compute the integral of the function Zn along this loop. So by the definition of the integral is the following. The loop goes from 0 to 2 pi. We replace z by the expression of the path here, r times the derivative. Times the derivative would be r okay. So this would be something like r n plus 1 I here integral from 0 to 2 pi I okay, and well, this is applying the usual rules of the real integrals. You can try to find the primitive here directly. So y, so divide by and this is 0. Well, this has the same value in this point and in this point, so this is 0. They have the same value because the exponential is periodic of period 2 pi I. So this integral is 0. Okay? So this integral is 0. We know this result there. We know that this integral might be 0 because z to the n has a primitive. A primitive is the function okay, it has a primitive, so the integral along any closed path in fact must be 0. Here you can see why the assumption of n different from -1, because we want the denominator not to be 0. What happens if the denominator is if n is equal to -1? So what happens if we take the function 1 over z? Over z is a function, holomorphic function, defined in z minus 0. It's holomorphic, And assume we have that path here, the round path around the origin. So this is a path defined in the domain of definition of the function. And what is the integral? The integral would be the integral from 0 to 2 pi of 1 over r to the it times war r e t. And this is, well, this is here. So you have I times the integral of 1 from 0 to 2 pi. So this is 2 pi I, this integral. Okay, in particular, this is not 0. It's not 0. So, as a first conclusion, we have that 1 over z does not have a primitive. Does not have a primitive in, because we have found a closed path such that along that path the integral is not 0. So this function cannot have a primitive. This is not any function. This is important in some sense. In the first lesson I spoke a little bit about the difficulties of defining the logarithm. Well, we want to define the logarithm. We want that the logarithm is a function, would be a function, holomorphic function, such that the derivative must be 1 over z. So the logarithm might be a primitive of this function. So as a conclusion, we can say that no logarithm can be defined over c minus 0. No holomorphic logarithm can be defined in the whole complex plane except 0. So we must take care about the definition of the logarithm, as I said before. We will say, perhaps not today, but in a couple of lessons, we will say where can we define, in fact, logarithms. But it's not in every open set, okay? Some sense. Okay, anyway, primitive implies the existence, the primitive implies that the integral along any loop must be 0. And primitive implies that the integral is independent of the chosen path. Okay, so the next question would be, assume we have a function. Could it be continuous? Could it be perhaps holomorphic? When does this function have a primitive? When does it have a primitive? Okay, does always have a primitive. So we know that a first condition in order to have a primitive must be that the integral along any closed path must be 0. If this condition is not fulfilled, we cannot expect to have a primitive. But is it enough? Or perhaps it's not enough. We find a primitive of a function. Well, if we reproduce the same arguments as in the real variables, in real variable, remember that you have a continuous, let's say continuous function defined over R or over some open or closed interval in R, assuming it is continuous. You know that this function has a primitive. How? Well, you can define the primitive as the integral from a fixed point to some x. And this is a primitive. This is the fundamental theorem of calculus. This is a function that has such that the derivative. Okay, so any continuous function, you know, has a primitive. We can try to reproduce the same scheme here. So, assume, for instance, you have some set here. You have a point, fix a point here, and you want to find the primitive. You have a function, and you want to find the primitive. So you could do more or less the same thing. We are going to integrate from z0, this fixed point, to another point z. So we're going to restrict to a particular kind of domains. So what are called, for instance, star-shaped domains for the moment. And a star-shaped domain would be a domain such that there exists a point, Z0, such that any point of the domain can be reached from Z0 with a straight line, with a segment. I mean, for instance, the most interesting kind of a star-shaped domain would be convex sets. Any convex set is in a star-shaped domain from any of its points. Okay, but in general, you could have something like this. I mean, you have a point here. You would have something, perhaps. Something like this might be some star-shaped domain. So it's not a convex set, but you can reach any point from here. On this point, Z0. There must be at least some Z0 point. The most important case, I insist, are convex sets. So, assume you have a complex, a continuous function, undefined, f of z, as the integral along the segment z0, z of the function f. What does it mean? You have to parameterize this segment. Okay, as I told in the first session, the parameterization you choose of the segment is not very important. But the usual parameterization of a segment, of course, would be something like this: 1 minus t z0 plus t z, where t takes values in the interval 0, 1. This is the usual parameterization of the segment. You follow the segment at not unit speed, but you at constant speed, and you take time 1 unit of time to arrive to the endpoint of the segment. Essentially is that. But you could take another parameterization of the segment. It's not relevant. Okay? So you could define this function here. How could you verify that this function, you could try to reproduce the same proof as in one variable to show that the function big F is a primitive of small f. How could you verify this? So, assume you have a function, a point z, and you want to see that the function big F is holomorphic in z, and the derivative is small f. So you have to try to compute this. Okay, you have to try to compute this. So you have a point here, z, and you take values z plus h close to, let's say, close to z.
I didn't understand this notation, z0 to z0.
To z, sorry. To z. Z0 to z. Thank you. It was a mistake. Z0 to z. Okay? So we want to see that if big F is a primitive. So we want to compute this limit, and this limit, and minus, for instance, a small f of z. We want to see if this tends to 0. But what is that? Here, this is the integral 1 over h times the integral from z0 to z plus h. And this would be the integral from z0 to z of the same function f. So the integral from z0 to z0 plus h, the segment, minus the integral from z0 to z. This is the point z. So take this integral minus this integral. If you want to imitate the usual usual rules of the real integral, you could like to consider this small segment here, and to say that this sum plus this integral here plus this integral here plus this integral here must be 0. So the integral here plus this integral here must be something like, you would like to say that this is something like integral of f from z to z plus h in this in. Okay. In fact, if a primitive exists, this integral must be 0 along this triangle, because this is a closed path. So if, in some sense, we have said before, the integral of, if a function has a primitive, the integral along any closed path must be 0, along this triangle must be 0. So if the function has a primitive, this must be something like this. So, well, this can be seen that this is the, let's say, called w here, the variable, not to put the same letter as here. So this difference would be something like this. This is a constant, so I integrate with respect to the variable w. This is a constant, so the integral of fz along this segment would be h. We divide by h, we have that. And if f is continuous, it is not difficult to see that this tends to 0, and we would have finished. But we need that the integral along this triangle is 0. If it's not 0, it's not possible to find that. So when does these integrals, take the value 0 along any triangle? So we arrive at one of the first interesting, let's say, interesting theorems that is called sometimes the Gusset theorem. Gusset theorem says the following thing: assume you have f defined on an open set U holomorphic, and take any triangle, T is a triangle contained in U. With a triangle, I mean the full triangle. I mean not only the border, let's say. I mean all the whole triangle is contained, not only the three lines, but the interior of the triangle is also contained, completely contained in U. This is a compact set. I include the borders. So this is a compact set completely contained in U. So then, and well, call for instance delta t the border of the triangle, the three sides. Then the integral of f is 0. If you have a holomorphic function, the integral along any triangle is always 0. Okay? As we can deduce from an example I said before, if this condition does not happen, the complete triangle is included in the open set U. It may happen, if this condition is not fulfilled, it may happen that the integral is not 0. For instance, we have shown before that if you take the function 1 over z, the integral of 1 over z along this circle here is not 0. If instead of taking this circle, we would have taken, for instance, something like this, a triangle here, Assume we could have taken these 3 lines. Remember that this function is not defined at the origin. So the interior of the triangle is not contained in the domain in this sense, in this case. Well, if we compute the integral along the border of the triangle, it's not 0. So in fact, it's the same. You obtain the same result as before. The integral here along this border is 2 pi I. You can compute. Okay? Exercise.
Also, C minus 0 is not a star-shaped domain.
It's not a star-shaped domain, okay? But in this theorem, Gusset theorem, I'm not assuming exactly. Now I'm not assuming that it's a star-shaped domain. I assumed that before to try to define the primitive. But here I'm not assuming that U is star-shaped. U, let's say, can be connected, any connected open set, but not necessarily star-shaped. So, but if the integral along, if you have a function, a holomorphic function in a connected domain, the integral along any triangle completely contained in the domain must be 0. This is not a triangle completely contained in the domain of the function 1 over z, because the point here in the interior is not in the domain. Okay? Of course, if we integrate the function 1 over z along a triangle here, far from the origin, yes, the integral would be 0. Would be 0. Okay? But here is not 0. In a sketch of proof of the Gusset theorem. I'm not going to give a complete proof, but at least a sketch of proof. A sketch of proof. Okay? So, what is the main idea? Consider this a triangle here, T. Function is defined someplace, and do the following thing. Divide the triangle in 4 triangles. Take the middle points of the sides and divide in 4 triangles. So the integral along your triangle, so you integrate here, here, and here, can be divided in 4 integrals. You in this triangle you integrate here. Let's say in this triangle here you integrate also in the counterclockwise sense. So integral here, here, and here. Here the same. Here, here, and here, and in the 4 triangles. You can do the integral along the 4 triangles. So the integral along T is the sum of 4 integrals. Let us observe that these interior sides have been followed twice. When I take this side in this triangle here, I take this side in this sense, but when I take this side in this triangle over there, I take the same, I integrate along the same side, but in the opposite sense, so they cancel. So finally, the sum is exactly the sum before. So, well, one of those triangles verifies necessarily, that such that the integral of f along the big triangle is smaller or equal than 4 times the integral along one of the triangles. I don't know which triangle, but take, for instance, of the 4 triangles, the one with such that the integral has the bigger absolute value. Okay? And you can repeat this procedure. This T1, you can divide in 4, and again, etc. So you find a sequence of triangles in this sense, such that the integral something like this. You can find the sequence of triangles, each one is smaller than the other one, and the intersection of those triangles must be exactly 1 point. This is a decreasing sequence of compact sets whose diameter tends to 0, so the intersection is 1 point. Intersection is 1 point, and F is holomorphic at this point. F is holomorphic at this point. Okay? F holomorphic at this point means that Fz is F Z0 plus the derivative, say, times Z minus Z0, okay, plus, well, as I told before, something like Z minus Z0 epsilon of Z, with the notation of the differentials. Epsilon is a function that tends to 0 when Z tends to Z0, given that F is holomorphic at the point Z0. Okay? So we have that. And the integral of F, continue here, the integral of F, remark that Fz0 is a constant. Constant has a primitive. So the integral of any function having a primitive along a closed path must be 0. F prime is F prime of Z0 is a constant, and Z minus Z0 has a primitive. So this part, the integral of the first two summands here is 0 along any closed path, in particular along any triangle. So this must be exactly the rest, so the integral of this function here. Okay? And well, this can be bounded by one property that I forgot to mention before. That is straightforward, is the following. If you have the integral of any continuous function along any path, a continuous function along any path, this can be bounded by, if this is a continuous function on a path that's compact, is bounded, the absolute value is bounded, so let big M be a bound of the modulus of the function f along this path, and times the length. Times the length. This is straightforward to show that this property is verified. Okay? So, what we have here is, this is smaller than, let's say, than the length of the triangle Tn times the maximum, let's say, of Z minus Z0. Okay? And the length of, let's say, and this can be bound also by length of Tn. This number here, we are in the small triangle Tn. We're in a small triangle Tn. So this number here, this in modulus is also smaller than this length, of course. This segment containing the triangle. For the maximum, let's say maximum of modulus of Sz, something like this. And the length of this triangle, when you pass from here, from one triangle to one of these smaller triangles, the length of the triangle is divided by 2. So the length of Tn is the length of T, time divided by 2 to the n. It's a square here. So we have this is something like 1 over okay, for n length of t square, well, this maximum. Something like this, must be. You have for to the n because we have the square here. So, using now this bound here, you obtain that the integral of t, along t of the function f is smaller or equal than 4 to the n, with this 4 to the n disappears, so it must be something like this length to the square to this maximum. In an appropriate sense, and this maximum tends to 0 when n tends to infinity. Because of the definition of, well, there are some things to verify, as is only a sketch of the proof, because the definition of the holomorphy, you have that, the properties of epsilon z, this is bounded, this tends to 0, so this maximum here tends to 0. So, I have shown from here that this integral must be 0. Necessary. So the integral of any holomorphic function along any triangle completely contained in the domain is necessarily 0. Okay, this is Gusset's theorem. Okay, at least a sketch of the proof of Gusset's theorem. There is a slightly more general version of a Gusset theorem that we will need at some moment, that says the following thing. We don't need exactly that the function would be holomorphic everywhere, but if you have, there is another version, more general version. Gusset's theorem says the following thing. Assume that we have a function in U, a z0, a point on U, and such that the function f is holomorphic in U minus z0. So there is one point where perhaps f is not holomorphic, but it is continuous. As you have a function that is continuous everywhere and holomorphic everywhere, but at most in one point. Perhaps there is one point where it's not holomorphic. Assume T is a triangle completely contained in U. Completely contained in U, as before. So, in that case, the integral is also 0. Okay? The proof is more or less the same. You only have to take some care about where is the point z0. If it's inside the triangle, if it's in the border, if it's outside, it's not a problem. Okay? If it's outside, it's not a problem. Integral is 0. But if it's in the interior, well, you can try to avoid this point in some sense. The only problem would be, if you see, if this point z0 would be exactly this point here, is what you need, that this is holomorphic. But if not, if it's not that point, the rest of the proof works more or less the same, and you can have to take some care about, in this case, how to avoid the point. But the proof is essentially the same. I don't want to give more details. So the integral is 0. So we have arrived to some interesting results. From here we can deduce some results. So consequence of previous result of Gusset's theorem, consequence would be the following one. Assume that U is convex. For instance, U, a convex set. A a convex open set, and F is holomorphic in U. Holomorphic. Then F has a primitive. Then F has a primitive. Why? Well, as we said before, in order to have a primitive, well, in this case, our set is convex. You can fix any point, Z0, and define the primitive of the function f, okay? And in this case, you can fix any point here. So, well, the only problem to have a primitive would be that the integral along some triangle here might be 0. If this integral is 0, the construction of the primitive applied as in the real case, and by Gusset's theorem, now this triangle is completely included. Of course, this is completely included in our convex set, and the integral is 0. So this defines a primitive. So any complex function defined on any holomorphic function defined on a convex set has always a primitive. Okay, so a second consequence is the following. Assume U a convex set, for instance, and F a holomorphic function over U. Assume gamma is a path on U. A closed path, a loop, a closed path on U. Then the integral is 0. It's always 0 along any closed path. If the function is defined on a convex set, not on any set, as we have already seen in the example of the function 1 over z. If the function is not, the domain is not convex, this is not true. The domain is C minus a point. We have a function, a holomorphic function there, and we have found some loop, and around that loop, the integral is 0. In particular, for instance, if we had considered the same function 1 over z, okay, we consider this function 1 over z, but is defined here, except here. But we take, for instance, any loop here, any loop here, any loop in the right half plane, any loop in the right half plane, the integral would be 0, because here the set is convex. In fact, it is not necessary that I said before that the set U is convex. This is well, the most usual case, but the result applies also if U is star-shaped. With respect to one point, the construction of the primitive, we only needed that U was star-shaped. So if we have some star-shaped domain, we have a holomorphic function in a star-shaped domain. This function has a primitive. The integral along any closed path must be 0. Considering again the example of the function 1 over z, well, another example of one-shaped domain could be a slightly bigger domain as the following. Remove the origin, of course, this is not in the domain, and remove any ray from the origin. Remove here any ray from the origin. So take, this is called D, this ray, including the origin, and take U C minus D. This is a star-shaped domain. For instance, with respect to a point here, this is star-shaped with respect to any point here. So the function 1 over z defined here, not in this line, has a primitive, and the integral of along any closed path is 0. So, but you can see that a closed path here does not go around the origin. That's the problem. To go around the origin, that is a bad point. So you have any pretty path here, the integral must be 0. But this integral does not go around the origin. Well, I always draw the paths like this, but a path can intersect itself. So a path can be something like this. This is not forbidden. This is not forbidden for a path. I always draw it like this. But also the idea is the same. The path must not, let's say, goes in this example goes around the origin. So, for instance, if the origin is here, this is not a problem. Okay. So only in order to finish, I would like to make a brief resume. Every holomorphic function defined in a star-shaped domain or a convex set has a primitive, and this is a consequence of Gusset's theorem, which says that holomorphic function defined in an open set U has zero integral along any triangle completely contained in the open set, and this is what we need to construct the primitive. And in fact, this implies that the integral of any holomorphic function along defined on over a convex set or a star-shaped domain, the integral along any loop must be necessarily 0. As a consequence, we know that there are some functions that do not have primitives. We will use in the next session all these facts to make a very strong relation among holomorphic functions and analytic functions. I mean functions defined as power series. And in fact, we'll see some striking results that makes one of the main first differences among the real cases and the real, let's say, C1 differentiable functions or even C infinity functions and the complex functions. Okay? So this is the end of the session.